Yeah. Hello. Yeah. So now that we have seen the mass timer, let's go to the stiffness timer. So as you recall, there is dimerization in the stiffnesses. That means so it's K1, K2, K1, K2, like that. The masses were not dimerized, so just N. So we can call this, let's say, U1 of I, and then this U2 of I. Free body diagram for first particle. Right, these are the forces. So if we write the Newton's second law, force is equal to net force is equal to mass into acceleration. Get so this is the F is equal to MA format. You can simplify this further. So this is the equation that we get. So what we have done is we have combined the equations that we got from the free body diagram of the stiffness diamonds for the first degree of freedom and the second degree of freedom. So this is for the first degree of freedom and this is for the second degree of freedom. So these two equations can be written in a combined fashion. Uh, Here the 2 cross 2 matrices the linear equation. Then the RHS can be taken to the LHS side, making this 2 cross 2 matrix into this 2 cross 1 is equal to 0. So if this is the equation, just like in the mass dimer case, and this is the standard procedure in fact, any multi freedom system. So it's like in the mass timer case, what we are going to do here is we are going to take determinant on both sides. Determinant of 0 is 0. That means determinant of the LHS has to be 0, right? So determinant of left hand side is equal to 0, right? So that implies a determinant of this matrix. So we can call this dynamical matrix. So this dynamical matrix, um, the determinant of the dynamical matrix has to be 0 because if u1 and u2 are 0, which is also possible, then we are not talking about wave propagation. Since we want to talk about wave propagation, we want to find out the characteristic analytical relations for that. The dynamical matrix has to be, the determinant of dynamical matrix has to be 0. So if we find that out, what we get is just like in the mass dimer case, even here we should observe a quadratic form. So let's say q minus q2 minus. If we write correct the omega power 4 terms, what we'll see is omega power 4 will come from here, so it will be m square. Then if we collect the omega square terms, we get is this omega square will be this into this, and this will this into this. So we'll get plus the remaining terms. That should be 2k1 k2 minus minus. This is the simplified version, of course. Yeah, now if we write the if we write the omega square, solve for omega square, then it would be of the form So again, like we have to find out what are the roots at q is equal to 0 and q is equal to pi by 8. So at q is equal to 0, we'll get one will be 0 and the other will be, let's call it omega t. That will be that. The other end, q is equal to pi by 8, we'll get 1 will be omega, let's say, let's say k1, let's say k1 is greater than k2. If omega is equal to, we call it the lower one. The lower one will be equal to k2 by m. Omega upper is equal to k1 by m. Yeah. So if we compare, uh, just like in the mass timer case, we had 2k by m1, 2k by m2, and if m1 and m2 were equal, then it m1, let's say m1 is equal to m2 is equal to m, we had these 2 points would come closer, and then we'll have band touching. We'll observe this band touching, like we'll code it and we'll see. Actually, we'll code only all the equations that we have derived. We'll sort of verify them. Um, so here, if k1 is equal to k2 is equal to k, then omega l is equal to omega u is equal to 2k by m. What is that? That is nothing but band matching. Now Yeah, so welcome back. So what we showed essentially is that that if you have a stiffness dimer, right, or if you have a mass dimer, so in both cases you can have band touch when whenever the dimerization disappears. then then it also implies if there is band touching, it's band folding. Yeah, this is useful in certain topological systems such as the stiffness dimer. We call the stiffness dimer as SSH. Uh, so is an SSH. SSH is named after three scientists. So Schreiber, Eager. So so polyacetylene. I think it's a polymer. So in that they were able to show that the stiffness dimer is an appropriate model. So they had something like molecules like this, then single bond, double bond. So this was equivalent to this. So this is also useful in topological systems where the stiffness dimer or the SSH is considered to be the simplest case of a topological system. So that concludes the dimers, right? And important to remember that all of this is through Bragg scattering. And what is the basis of Bragg scattering? Effectively, periodicity. So we know that periodicity, which is inherent in a crystal, leads to Bragg scattering, and Bragg scattering leads to band gaps. That means that every crystal will have band gaps because a crystal is fundamentally periodic. That means that every crystal will have band gaps. So, so then, so if every crystal is going to have band gaps, then yeah, uh, why haven't they been discussed maybe before? So, or why are they not that applicable in certain uh, fields? So typically, what happens is that the band gap, the first band gap, it might be at a certain frequency. So let's say if you are not at all dealing with that frequency, if you're dealing well below that frequency, so this this is your Williams zone. Like if you're only dealing with this area, like very low frequencies, then you may not even realize the curvature which is happening due to dispersion in the omega cube plot. So, so it depends on the, although everything is discrete, but it depends on the scale of the phenomena that you're going to observe. So if you really want to make use of the discreteness, you have to deal with you have to match the wavelengths with the discrete scales. So that is the advantage as well as the limitation of Bragg scattering. That somehow there is a scale matching that is going on, right? So Bragg's condition is uh, lambda is equal to 2a, right? So this is fundamental in creating all Bragg based band gaps. Is there some other way, uh, that we could create band gaps? We know that Bragg is based on reflection because this is the incident wave, there's a transmitted, and something is reflected back. Then, if it is Bragg, then reflectance is typically high, right? But is there some other way of uh, making sure that transmittance is low? So one way is that this is reflectance, incidence, this is transmittance. We know that in Bragg, reflectance is high. What is the other way that we can stop transmittance? The other way is other idea is absorption, right? So how do you absorb? And mind you that we are not talking about any damping, so we are not talking about dissipation. There is no particularly energy absorbent material that is placed here. So whatever is going to absorb the energy, that has to be part of the crystal. We take inspiration from, let's consider base excite, excitation. Consider base excitation. Let's say this is the base, and there's some spring and there's some mass. Let's say the base is x and this mass is y. Let's say we need to find the amplitude. So let's say x as a function of time is equal to some capital X into some e power I, uh, omega t plus phi x. Then y as a function of time is equal to, let's say, y I omega t plus, let's say, phi y. So what we are saying is that if the base is excited with an amplitude x, and this is the harmonic, then the particle, let's say it's m, is k, then the particle uh, is excited by y, and the frequency with which, and we're talking about steady state, right? So this is steady state. We're talking about steady state. So so what happens to the ratio of y by x? If you plot y by x, right, as a function of omega, then what you notice is that let's say let's say omega is like really low. Then what happens? Then essentially the base is moving very slow, and the spring K and the mass M, they have enough time to make adjustments. And what happens because of that is how much ever the base goes up, the mass goes up by the same amount because it's so quasi-static almost. So when omega is close to zero, this value has to be one. Right? Now what happens when, let's say, omega is really high? When omega is really high, and the x is being excited at really high frequencies, and there is certain inertia in the mass, and the stiffness is also limited. So they won't be able to react that fast. If if it is too fast, then what we'll notice is that the mass m actually stays stationary. Um, and then so at infinity we know that like yeah, as the more we approach infinity we know that yeah, y by x is also decreasing. But there will be one frequency where y will shoot up. Let's say there's no damping, there will be some frequency. This y just shoots up to infinity. This is approximately the curve that we typically know. What is this frequency? This frequency is nothing but the omega naught is equal to under root k by m. So what is omega naught? Omega naught is resonator frequency. Now, what is the resonator frequency? So, so basically, what we are saying is that when the external excitation matches the resonator frequency, the resonator goes crazy. The amplitudes become really high. So you might have observed this in your washing machine. Let's say when washing machine is in the spinner mode, notice that when it starts spinning initially, the washing machine is quite stable, right? And the omegas are low. As the omega increases, the washing machine sort of starts wobbling a lot. There's a lot of excitation. There will be some frequency where there's a lot of excitation, but as it speeds up to a frequency greater than that, as it speeds up further, we see that the wobbling slowly decreases. At really, really high spin frequencies, the washing machine does not wobble much. So in this scenario, we can think of the we can in this scenario we can think of uh, yeah, hello, yeah. So in this scenario, we can think of the washing machine as the resonator and the inner motor as the uh, base excitation. Sort of. So when base excitation matches the resonator, then the resonator goes crazy. So we can use this principle somehow. So it's used. How is it used? Let's see. Let's say let's say you have a crystal like this. Inside you have some hollowness. Then you connect this local resonator. Why are we calling this local resonator? Looking like a pokeball. We call this is local resonator. Local resonator because it is inside each unit cell. So that is where the locality of the resonance comes from. See, fundamentally, if you have a chain and let's say if you find out the um, eigenvalues, it will give you the frequencies of how the chain will basically resonate. So all the modes are resonances. Uh, so so in a way, all eigenvalue problems they are talking about resonances in some way. But at what scale are those resonances happening? That is crucial. These resonances are happening at each unit cell level. That's why we call it local resonance. The local resonance is brought upon by these local resonators. So let's say this is k by 2, this is k by 2. Oh, wait. So, so these springs can be, let's say, capital K by 2, capital K by 2, capital M. Then omega naught is equal to under root capital K by capital M. Right, so let's say we place this inside a unit cell. Now, if you think about it, what is the base in this scenario? The base is this little mass M, this hollow one, that that forms the primary degree of freedom of the unit cell. So that mass acts like a that mass acts like a base. So M is the base. So that means when M is vibrating at omega naught, the local resonator will have almost infinite amplitude. But is this possible? If energy is finite, then there cannot be infinite amplitudes. That essentially means that at omega naught, M is not vibrating because it's about the ratio y by x. So if y cannot be infinity, then for the ratio to go to infinity, x has to be 0. That means if M cannot vibrate at omega naught, there must be a band gap at omega naught. Ah, interesting. So originally we had something like this, then we added local resonance omega naught. Then let's say omega naught is somewhere here. Okay. So how will this look like? We know that there has to be a band gap around omega naught. Definitely at omega naught, but around omega naught, something will there has to be a band gap. So we'll investigate that. Let's start by writing the identifying how many degrees of freedom exist. So this is the unit cell, and inside the unit cell, the first particle is small m, the base particle. That's your 1 degree of freedom. And the other particle is the local resonance. And they are both independent degrees of freedom, although they are connected by springs, but you can hold one and move the other. So they are independent degrees of freedom. That means local resonator based systems, they are 2 degree of freedom systems, just like a dimer. So we expect that since it's 2 degrees of freedom system, we expect there to be at least one band gap in between and one cutoff frequency, just like the dimer. However, we'll see that this is going to be fundamentally very different from the dimer case. So let's begin by drawing the free body diagrams. Okay. So free body diagram for M. Right, there are two springs. Okay. And so what is this spring pulling it with? Let's say the degree of freedom is U2I, and for the shell is U1I. It will be K by capital K by 2 U1I minus U2I. Really in this direction, K by 2 U2I minus U1I. We combine these two. What do we get? get M U2 mass into acceleration is equal to A U1 I. It will be, this one will be similar to the monomer case. However, the local resonator is also acting on the base mass. So this will be Q1 of I plus 1. Similarly, there will be something here that will be mass into. Okay, let's just write it from simple. Just draw the free body diagram. I think it's not complicated unnecessarily. But you'll see that the local resonator also applies a force, let's say. Awesome. We have two equations. Of course, we have to write this. Now what we'll do is we'll of course combine these two. So we take the stiffness matrix to the other side. What we get is This is a bit complicated, so just write down. Um, I would encourage you guys to check the results nonetheless. I keep forgetting what notation I'm using. So again, this is a quadratic. Yeah, as you can see, so the band gap that is opened, it will be opened at omega naught, so at that frequency. Um, Irrespective of what um, the other mass is, the other stiffnesses are, um, the lattice constant A. One thing is for sure that there will be a band gap at omega naught. How broad it will be, that will depend on all the other factors. So broadness depends on other factors as well. So particularly, um, it depends on m by m. We call this coupling strength. So what is really coupling is that the local resonant mode is coupling. Say you have something like this, plus you have a high attenuation here, plus let's say you have a, this is the main chain. Right. So you combine these, they both couple to form this plus this, where you have a zone of really high attenuation. So this really high attenuation, this will be covered. Again, we'll go into some coding and you'll see that zone of high attenuation. Let me just share some results regarding the locally resonant materials. I hope the screen is visible. So yeah, so what we see here is that yeah, here we see that so this is the local resonant gap, right? So some parameters are being changed, and we see that whenever, so this gray line, horizontal line is the frequency of local resonator. So as the frequency is increased, you see the band gap wherever it opens is also changing, and the broadness of the band gap also changes. Typically, the lower the band gap is open, the narrower it is, and higher the band gap is open, the broader it is. This is for a higher coupling ratio. I think gamma is the coupling ratio. So even though it is low, it is still broad. It's for even higher coupling ratio, that M by M we talked about. So again, although it is narrow, it is still broad, and the higher band gaps are even broader. So that's the effect of coupling strength on the band gaps that is opened in locally resonant systems. This is the reference by S. Huber from ETH Zurich. So yeah, he has notes. I think I'll share those notes. They're amazing notes. Best notes. I'll share. Yeah, back to our system. I hope the yeah, I hope the locally resonant band gap has been demystified a bit. Yeah, so if you just write, if you just find out what is this omega upper and this omega lower, you just calculate that, see that omega lower equal to 2k capital M plus 0.5 capital K M plus M minus under root 2k capital M plus 0.5 capital K M plus M whole square minus 4 M M K K M1 M2. So this is omega lower, quite complicated compared to, let's say, the dimer case, where I think these were quite simpler forms. That's why those are standards for some systems like topological systems. Now, if you see the upper band, that would be the upper band, and then omega cutoff. If you try to plot, omega cutoff will be equal to basically basically this, but instead of minus here, we'll have plus. So yeah, same thing, but almost similar in form. Yeah, so these are the frequencies. Yeah. So now, so far we have covered Bragg-based systems. We have covered local resonance based systems. Uh, then within these systems, if you notice so far, like what we have done is we've assumed some chain like this, some unit cell, some connection, some unit cell, some connection, something like this. Now, what if, um, but this is like free, right? What if, uh, what if it's connected to some base? What if everything is connected to some base? Like we call that grounding. Let's say some unit cell connected to the adjacent unit cell, right? Further, it is connected to some ground. This is also connected to some ground. This is also connected to some ground. So what is this? This is called grounding. So it's important to realize that in reality, depending on how we are using certain materials, like where we are using, we need to not just see the connections between unit cells, we also need to see how the unit cells might be connected to some potential. We call it on-site potential. So on-site potentials can totally change the way waves propagate, and we'll see. And accordingly, some systems need to be developed uh, accordingly. So let's say, let's consider the simplest case, grounded monomer. So we'll consider a grounded monomer. Now, what would that look like? Right? Some chain repeats like this. And typically this would be the unit cell. But we have some sort of connection like this. Like, let's consider this as a rigid rod or something. This is some rigid rod. It's connected to the ground. This is Kg, grounding stiffness. Now, did this um, increase the degrees of freedom? The answer is no. So it does not increase the degrees of freedom, but it will still influence the the dispersion properties. And for that, we have to, of course, draw the free body diagram this time. Free body diagram of grounded monomer. So, by now, I'm just drawing the free body diagram because we've drawn so many, I think. There is no need to explain it in such detail, right? And then this will be K grounding minus what is the displacement of ground? Zero. Okay. And yeah, this is mass into acceleration is equal to, this is the block flow K condition that I'm imposing on these. This is because of the harmonics. Yes, if I write it, I'll see it in this form. So what we'll notice, what we'll notice here is that if I take this to this side, then I take mass to this side, and then I simplify this by writing it in terms of cos. Right, so this is the equation that we get. Now for the maximas and minimas, what we have to see is at q is equal to 0, what happens is it becomes omega is equal to under root kg by m instead of 0. This is important. Earlier, the lowest branch was starting from 0, but because of grounding, what is happening is the lowest branch will start from under root kg by m. And we'll visualize this. You'll understand why it is starting. So from the mode shape, we'll understand it. Q is equal to pi by a. Essentially, what you'll see is you'll see that omega is equal to will be 2, bracket will be 2, then 4, 4k plus kg by m. This will be so. So this entire region, so this is a band gap. This this is the cutoff. And This is the region that is passband. So what we see is when you have a grounded system, you have a band gap starting from zero. And let us visualize why it is happening. Uh, Let us visualize this mode. So now imagine this is in phase, right? It's in phase. This is out of phase. Now imagine if this is your chain. So why was the in phase mode at zero frequency? Frequency. So why was the in phase mode at zero frequency? If you think about it, for really long wavelength, which implies wave number is really low, all the masses are having almost same displacement. When they have the same displacement, what is the restoring force? Because when this I and I plus 1 and I minus 1. So when I and I plus 1 both move by the same amount, there is no potential energy stored in the spring K. Similarly, when I and I minus 1 move by the same amount, there is no potential energy stored in uh, the spring connecting them. So, and you can think of it in, if you see harmonics as an exchange of potential energy and kinetic energy, you could understand if nothing is going from kinetic to potential, then there's like there's no harmonics essentially. So frequency is zero. It's a rigid body motion. Um, Similarly, if there is no restoring force, then yeah, you can't have harmonics. So that is the problem uh, with the in phase motion. Uh, that is why it is zero. It starts from zero, and as Q increases, omega increases. But in grounded systems, when the entire chain is moving, what is happening is now the entire chain is grounded. Everywhere the chain is grounded. Everywhere. So what is happening is there is a restoring force in the grounding stiffness. Right? There's some potential energy stored in the grounding stiffness. So for in phase Q is equal to zero mode, the grounding stiffness provides restoring force. So when the grounding stiffness provides restoring force and the stiffness K which is connecting adjacent unit cells that is not even strained. That is why in the frequency equation we see the it is omega is square root of kg by m. Whereas in the out of phase motion, we see k popping up here. That is what is unique about grounding. And essentially, if we are looking for band gaps, And first we need to ask, is our system grounded or not grounded? If it is grounded, then that's like job done. You have a band gap from the start. You just increase the grounding stiffness, and it'll push your minima up. So that is the beauty of grounding. Okay. So you can ground various systems. You can ground every system, in fact. So we spoke about acoustic mode, right? So let me say grounding will tend to push all modes higher, but it is particularly noticeable in the acoustic mode, which starts from zero frequency. These are the key points for grounding. Now, if you have any system, let's say if you have a dimer, so this is what we were getting for a dimer. What if you add grounding kg? We expect that we'll see something like this, some shift upwards for all modes. By exact what amount will depend on the mode shape, but we expect to see grounding pushing up all the modes. And the same thing we expect in locally resonant systems. Even in the locally resonant systems, we can have grounding. So I'll leave you with one question for grounding is what is the type of band gap for grounding? Because we established that there is something called a Bragg band gap. So we can maybe write it down. What is the type of band gap in grounding? Option A, is it Bragg? Option B, is it local resonance? Option C, some sort of, I don't know, something else. Something else. So is it Bragg? Hmm. So we'll cover this in the next lecture. Let's just recap. Now I'm just recapping what where we started today's. Udbhav, you're there? Yeah. So,
Yes.
oh, UV. So this is a question for you. Okay, interesting. Yeah. So we established that grounding will push up the in phase mode as well as the out of phase mode by different amounts, of course. But yeah, um, maybe if you see it in terms of omega squares, then yeah, it will push them up in equal amounts. I think we could say that. Then if you see in terms of omega square, then grounding pushes everything up by plus kg by m. We could say that. Could we?
Yes.
Okay. So so earlier there was no band gap here, but now there is a band gap now. So and my question is, what is the type of band gap in grounding? Is it Bragg? Is it local resonance? Is it something else? What is it?
Um, it's not. I don't think it's local resonance
Mm-hmm.
because uh, it could be local resonance because we are shifting something like so a grounded can be understood as like if you have a mass and mass resonator
Mm-hmm.
and that resonator mass tends to infinity. So
Okay.
I think, yeah. So
So
I
you're
will
saying
say
that okay, that's a very good analogy. So what Udbhav, for everyone who's attending, is saying that so if this is your outer shell,
yeah.
and let's say you have something like this. Typically, this Pokeball is your mass and mass system for local
Hmm.
resonance.
Yeah.
But let's say this is capital M, this is small m, and then there's some connections. Now, if you if you if capital M tends to infinity, is what you're saying,
Yes.
then it's a very good question, a very good answer. Then essentially what you're saying is that this is grounded here. Then then in that way, if we analyze the local resonance frequency, omega naught will be equal to k by m. But we know that m tends to infinity, then omega naught is equal to 0. So grounding could be thought of as a local resonance where the resonating frequency is at 0.
Whoa.
We have to verify it. We have to see if it's the attenuation profile.
No, but okay. It because at zero you have your that now. What do you say? Uh, okay, okay. It's like so sort of like if you have a resonator band gap and
Hmm.
let's say your resonating frequency is k by capital M. So if you put it at zero, um, Yeah, I have. I think. Hmm. The mass is negative for some. What's the like I think I missed that profile thing. Yeah, I think we have to look into that. But so I'm assuming it will be, that attenuation profile. It
Yeah,
will
so
be
okay, so typically what we discussed was that if the omega naught value, if it goes down, then the band narrows, right?
hmm,
But there's something called coupling strength. Uh, so coupling strength is the ratio of mass of the resonator to the main mass. If you increase that, then although the band gap is narrow, if the
it
band gap is lower,
widens
it will
basically.
widen,
Hmm.
right? So
Okay.
essentially what you're saying is grounding is a, so if also if you look at coupling strength, it's a very good answer, Udbhav. M by M
Thank you,
tends to
sir.
infinity. That means grounding is an extreme case of local resonance.
Yeah.
Yup, brilliant. But there is a trick. Things are not so straightforward, of course.
Yeah, yeah. Sir Rajesh sir told me. Yeah.
It's not that simple. So, so we'll see what's the trick. Uh, so the trick is if you really go into extremes, you could even relate Bragg with local resonance. Like a local resonance gap in an extreme case where
Mm-hmm.
singularities are involved is essentially just a Bragg gap. Does that sound
Okay.
interesting?
It's sort of a mixing of Bragg and local resonance, right?
I'm saying everything is a mix.
Oh, even like uh,
Every
even the
band is
Bragg
a
band gaps.
percentage,
Hmm.
sort of. Uh,
Okay.
Maybe not, but at least you could say every local resonance has an element of Bragg in it.
Yeah.
Every Bragg does
Yes.
may not have a local resonance in it, but every local resonance has an element of Bragg in it.
Yeah.
So there's
Got
no
it.
pure local resonance because you cannot remove the periodicity of the crystal. Bragg is always going to be there.
Uh,
Bragg
but
is
the but
yeah
the question is now, like, so Bragg band gap is all about like interference of waves and all.
yeah
Um, Local resonance, as the name suggests, na, it's opens a like a small narrow uh, band band gap.
yeah yeah. In that
It,
case,
mhm.
why is the local resonance gap following like why is the band gap still starting at q is equal to pi by a? What relation does q is equal to pi by a have in a local resonance gap? Let's say you observe something like this.
Mm-hmm.
Although although it starts here, but although like yeah, it starts here at q is equal to pi by a is still the criteria for opening the band gap.
Yes.
Why?
Uh, so that q equals to pi by is sort of the thinking in terms of the wave numbers, and perspective. Um like it's a beginning of the out of phase motion, like in a way, across unit cells.
It's an out of phase standing wave, right?
Yeah, standing wave. Yeah.
It's a standing wave. It's an out of phase thing, and that is
Hmm.
what Bragg condition is. Like if you, that's what we saw. Bragg condition is lambda is equal to 2a.
Ah,
Is
okay,
that?
okay.
Yeah.
Yeah, yeah. Yeah.
Bragg condition is lambda
Understood,
is equal to
understood.
2a.
Yeah.
Essentially, that's what Bragg is also trying to say, that when you have completely out of phase, when you have completely in phase, and you have completely out of phase, those two standing
Hmm.
waves, essentially we are looking for standing waves as cutoffs. So that is
Yes.
one way to maybe look at it. Maybe we could write it down. I think could say, you know, standing wave modes are the cutoffs. So we spoke about the, that is why the non-local thing might be standing out. Pun intended. So
Yes.
where standing waves are formed not at cutoffs. Typically, standing wave modes are the cutoffs. Okay, so yeah, what do we have here? Okay, let me just share my screen. I'll show you why local resonance can be drag. I thought I'll leave it for the next one, but why not just extend this session? Can you see my screen?
Yes, zoom it in a little bit.
So if I zoom it,
Yeah, correct zoom. So,
okay,
yeah, it's barabar zoom. Yeah.
zoom, barabar, okay.
Yeah, yeah.
Okay, so see this gamma is coupling strength. So what they are saying is, if coupling strength is low, when the gap is narrow, when the gap is low, the opening is narrow. If you keep it low enough, but if you increase the coupling strength, you can broaden it, right? That's what they're showing, broadening. So this is the first column. But in this, along the row, what is happening is the resonating frequency is being increased. So at higher frequencies, you get
Mm-hmm.
broader band gap, sort of. Right? It's happening everywhere. As you go higher, it's broader. The more the coupling strength, everywhere it's more and more broader. Cool. Now the thing is,
Yep. Cool.
what happens when? So how are you? So when you say you're increasing or decreasing coupling strength, you're basically messing with mass. And when you say that you are increasing the resonating frequency, you are sort of tuning the stiffness, right? Now, for if you keep the
Yes,
same
yes,
mass and if you
yes.
keep stiffening the stiffness, what will happen? You keep stiffening it, and ultimately you reach fully rigid spring,
Yeah.
right? The optical band, the band above, will keep going higher and higher and higher, and it will disappear into infinity.
Hmm.
And if you think of your unit cell, your mass in mass system is that inner mass is connected rigidly to the outer mass. That means it's not an independent degree of freedom. It's a monomer.
Yeah. Yeah.
You now have a monomer where your total mass, instead of, let's say, small m, now it is small m plus capital M. That is your total mass.
Mm-hmm.
and you have only one band
So
inside,
yeah,
right? So what that means is,
that resonator sort of it is like we can say it's a brag.
yes, so
Like
brag
uh,
is there,
brag is always there.
especially the lower cutoff. You see the one at
Uh,
pi by 8.
yeah,
It's brag influenced, and we see we see it as purely brag when we totally push the resonance frequency to really high this thing. Then we so ultimately in metamaterials, in dispersion curves, most of the answers to if is something this is something that actually depends on the frequency range of interest. Let's say let's say you have this last case, but if your
hmm,
frequency range of interest is much below the local resonance frequency, you can pretend like that is a bragg cutoff. In reality, if you think about it, even if you try to make discrete systems, they will have internal resonances. They are made of realistic masses. They are made of, so they'll, right, if you have a solid cube of whatever, they will have internal resonances because there will be, you know, infinite modes internally.
yeah,
So in a way, everything is local resonance. Even your spring will have some mass and it'll also have some internal resonances. And that way everything is local resonance. But if those local resonances are very high, everything is bragg. So it depends on your frequency of interest, what is local resonance, what is bragg. If within your frequency of interest you have something, some particular attenuation profile, some particular modes, then you classify it as local resonant, bragg, such things.
yeah.
Same with grounding. So yeah, grounding is an extreme case. If that's a instead of perfect grounding, let's say, yeah, it could be partially grounded in some way. I'm thinking of, I don't know, like how exactly, but if there was some way of partially grounding it, there would have to be a smooth transition.
Yeah, yeah. I mean, you will see then, I think, according to me, I think if so by a partially grounding, you mean that it's not a rigid wall, right? I mean, it has
Yeah,
some like still a considerably high mass, but yeah, like there is a finite mass. So
yeah,
I think we will see one band sort of rising from omega equals to zero, and like it will be more or less like, yeah, like the figure that you're showing on the left side and right now,
yeah,
that
yeah.
yeah, some band will raise and the upper band will come down or something, like yeah, something around those.
Yeah, or it could be multiple bands, but all within that range. We don't know the structure of grounding,
Huh, yeah, 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 yeah,
but everything will
understood.
be like very low. So yeah, so that way, if we are look, someone who's interested in those lower modes, for them these higher modes are cutoffs. Whereas for someone who's interested in these higher modes, the lower modes are almost grounded modes.
Yeah.
So I think yeah, that was a brilliant discussion.
Hmm.
And like always, I think you can always think of, wait, how much is the, I think the lecture has gone.
2 hours 40 minutes.
Yeah, yeah. Stop recording.
I would say for 20 minutes you can continue, right? Make it 3 hours. That will be
It's 3 hours, 18.
Okay, here for me it's showing 2 hours 38 minutes.
Yeah, but there was 1 hour something of previous, no?
Okay, joined late. Sorry. Yeah, yeah.
Yeah,
Okay, no, that's fine.
it's 3 hours 20 minutes, even if you take some 10 minutes in between when I stopped recording. So I think
Yeah, so
3 hour
10
20.
minutes
I
we
think 3 hour
can
20 is fine.
discuss. Uh,
Yeah, let's just
10
discuss.
minutes we can discuss.
Okay, stop recording. अब बता.
नहीं नहीं, it's recording.